Did y'all enjoy your snow day? Yeah. Seemed like the first day should have been the snow day, and yesterday should have been AMI. There wasn't hardly any snow on the ground by yesterday.
It was just because.
Do we have like a snow day we could use, or does that go into our summertime?
Snow days add to your summertime. AMI days do not. That's why I always prefer AMI, but I don't know. I understand some people are out of power and stuff, but I think most of your teachers are usually pretty flexible and give you some time to get caught up. But whatever. I don't get to make those decisions. Okay. So this assignment, I was actually going to have you guys turn in something different, but I need you to be at the same place as my 8A class. And for 8A, this is what I had them do for the AMI day. So we need to talk about what it means to be continuous. You need to know the definition of continuity and practice it a little bit. And I'm going to have you turn in these worksheets that we're going over right now today, since that's what I picked up for their attendance. And at first glance, it may seem like this is different than what we've been doing, and I guess in a way it is, but it really is still tied to limits. You just have to kind of stick with me here for you to see how that goes. Okay, so this one is 73, and 2 of the pages make up 73, and then 2 of the pages make up 74. The practice on 74 is actually like, I don't know, the questions are just super big. I tried to make them a little bit bigger to make them easier to see, and I think it still didn't work that great. So we'll have to talk about, make sure you know what the questions say. But so continuity is really about, is a function continuous or not? So usually it's pretty easy to just glance at a function and see if it's continuous, see if it's got any breaks in it. But the 2 big ways that you're going to have breaks in the graph is when you have holes. A hole is a type of break in the graph, and or asymptotes like this. That's a break in the graph as well. But in calculus, we need to be able to justify how we know something is continuous at a certain x value, or be able to justify why it's not continuous at a certain x value. We can't just say, well, there's a break in the graph. That's just not mathematical enough. So I could just tell you what the 3-part of the definition is and then use it a few times. But before we do that, on this first page here, I just kind of push you in the right direction to hopefully help this stick a little bit. So just kind of a little bit of discovery here. Continuous at x equals -2. Does it look like it's continuous there? Okay, so I'd say yes. So question 2, if a function is continuous, does that mean the limit exists at that point? So does the limit exist here? Yes, because it approaches the same thing on the left and the same thing on the right. If it was approaching something different, like if this was approaching 2 and this was approaching 1, do you see how that would be a break in the graph? It would be a little bit of a jump. So the limit does have to exist. That's one of the conditions for our function to be continuous at that point. Okay, what about x equals 2? I agree, and it's not the best graph, but there's a hole there. So if the limit exists at a point, does that mean that it must be continuous at that point? Well, notice this limit does exist. What it approaches from the left and from the right is the same, looks to be 2. So just because the limit exists doesn't mean it's continuous. It has to exist for it to be true, but just because the limit exists doesn't mean it's continuous. There's more to it than that. All right, number 5. If a function is continuous at a point, must the function be defined at that point? Why or why not? Well, we just kind of saw that right here. Well, actually, I'm lying, because there is a point down here. So if we just had a hole in the graph, would that be continuous? No, that would certainly be a break in the graph. So if a function is continuous, must the function be defined at that point? Yes. So for the why not, I'm just going to draw a picture. If you had a function and the point did not exist there, I'm going to use a. A is just like some generic x value. Then that's a break in the graph. So if it's continuous, then we know the point has to be there. Okay, and then the last one with our little picture at the top, does your graph look like it is continuous at x equals 1? I agree. That looks to be a no. So what I'm trying to get you to see out of this one is just because the point is defined, that does not mean it is continuous. There is a point, there is a value for at x equals 1. Right here. But because it's not over here, it's not continuous. Your graph can't just jump up for even just an instant and expect it to still be continuous there. So within that, we kind of saw some examples of where the definition comes from, a three-part definition. So from questions 1 and 2, we talked about, or 1 through 4, the limit must exist. And I think this part may be on your next page, I'm not sure. But the way we say that, so as x approaches some value of a, so a is just in the point we're interested if it's continuous at, it has to exist. And we'll look at an example of what happens if it doesn't exist. Okay, so that's what we got out of the first couple, is that your limit needs to exist. The next one, we saw that if you just had a hole in your graph, it's not continuous. So we saw that the point must exist. There's got to be a point at that x value. Again, I'm just using a as some generic x value. But just because the limit exists and just because the point exists, at the very end here, question 6 and 7, at x equals 1, there was a point there and the limit existed there, and we still said it wasn't continuous. So the problem was, even though there's a point and even though there's a limit, this isn't in the right spot. We need this to be right here. So specifically, what we will say is that whatever it's approaching from the left and right, which we call the limit, needs to be the same as the y value at that point. So you can't just have a point at that x value. That point has to be plugged into the right spot. So that is the three-part definition.
What does the last one mean again?
What?
What does it mean? Like if you had to put in words, can you say it again?
This?
This.
The point that exists has to have the same y value as the y values that it's approaching from the left and from the right. Whatever it's approaching from the left and whatever it's approaching from the right, your y value at that point has to be right there too. So, to try to really emphasize this, now again, unless we change the test, I believe this was a question on our test last year. What is the three-part definition? You certainly have to memorize that for calculus. We don't use it throughout the year, but it is an important part of the first unit. But to really try to hone in on this, I would like us to draw a couple quick examples of what happens if this is not true, what happens if that's not true, and what happens if this is not true. So it's not anything really different than we saw on the first page. I'm just trying to focus in on it to help you really see what's going on here. So if I'm trying to test to see if it's continuous at x equals a, if the limit doesn't exist, that means it's approaching one thing on the left side and a different thing on the right side. Certainly not continuous. That's why that first part of the definition is important. The limit's not the same, your graph is jumping around. The second part says that the point has to exist. So you might have a nice continuous function, but if there's a hole there, if that x value does not have a y value that goes with it, then you have a break in your graph. It is discontinuous or not continuous. And then the last one's usually a little bit harder to wrap your brain around, but just because its limit exists, it's approaching the same thing on the left and the right. And just because he has a point, if the point's not right here, it's not continuous. If the point's way up here, then that's not good enough. So that's why we need that third part. We need to make sure that this is actually equal to this. So these are just like some counter examples to show you what happens if that's not happening. And of course, that's a break in the graph. Your graph can't jump up at an instant and be considered continuous. Okay, for our next graph, if we just kind of eyeball this real quick, which of these x values would you say is not continuous at for question 11? What is one x value that's not continuous at? X equals what? 1. I agree. There's one of them. Okay, also 4, not continuous. I see 2 more, but 1's kind of hard to see. Okay, good. -2 is the hard one, and that's kind of my fault because of the graph. That's supposed to be a hole right here. And then last one, 2. So again, it's usually pretty easy to just glance at it and see, oh, it's continuous here, it's not continuous there. But as you'll see on the last page, sometimes we need to explain how we know it's continuous or how we know it's not continuous. But before that, you do need to know different types of discontinuity. So of these that we've got going on here, there's a jump, an infinite, and a removable. Well, jump is usually one of the easier ones to remember because it's where your graph is jumping. So that would be x equals 1 and x equals 2 are referred to as jump discontinuities. If your whole graph jumps, it is jump discontinuity. Which one of those do you think is infinite discontinuity? Good, 4, because at that discontinuity is going to infinity and negative infinity. That's why it's called an infinite discontinuity. And then the one that calculus students usually forget because we don't use it much except in the first unit, but then they have to re-remember it. One called removable discontinuity. And removable discontinuity is when you have a hole in the graph, which would only be at x equals -2. Sometimes students think maybe x equals 1 is removable because there's like a hole here, but since the whole graph is jumping, it's actually jump discontinuity. So make sure you put the word hole with removable discontinuity. The other two are pretty intuitive. There's also another one called oscillating discontinuity. You don't really need to know this one, but if you do go high enough in the calculus, if you ever pursue like a math degree or something, you would learn about this. But if you have a graph that zigzags back and forth fast enough, then it can be discontinuous right down at the middle. But we won't test you on that, and you don't even need to know that for calculus. I just like you to know that it exists. Okay, so a couple of the question types I'm going to have you guys do is practicing graphing a piecewise function. So as I mentioned, I guess it was last week, piecewise functions and reading those is certainly one of the things that holds back calculus students, and it's just an algebra topic, so I don't want that to be the case. I gave a test right before the snow in calculus, probably the hardest test we do all year, and I would say probably the most missed multiple choice question boils down to not the calculus skill, because students get the calculus part on another question, right? But just dealing with the piecewise function part of that question. So we need to review some of that for us. So sometimes our graph is going to be y equals negative x squared. So you guys know what x squared looks like, and then the negative just flips it over the x-axis. But really all of this is not part of my graph. Why do I not want to keep all of this? Right, because we only keep this part of it. You got to read the whole piecewise function. It's only y equals that when x is equal to 0 or less than 0. So we only keep the left half of it. The other times, y equals x, so where the line where x and y are always the same thing, but we only keep the part of it where x is greater than 0. So greater than means you don't include that point. That's an open circle. Greater than would be to the right, so we shouldn't keep any of that to the left. If you can graph those two parts individually and you can read your inequality here, then you can see what f of x looks like. All of this is the piecewise function. Part of this one, and actually I'll keep them colored. The red one, that part of the red one, and that part of the purple one makes up the whole thing. Okay, so once we do that, we could, I don't know, I feel like A, B, and C are kind of gimme questions, but D is the one I'm really interested in. But we could think about the limit as it approaches from the left and from the right, and if the limit from the left and the right are the same, then the limit as it approaches x, as x approaches 0 would also be the same.
So do we count 0 as being part of the graph, even though the purple one's 0?
Yes, because it still hits it from this one.
Okay.
So as long as it hits it in one of the two, we keep it. In fact, it can't hit it at both. If it hit it at both, you know how functions have to pass the vertical line test? It would really be hitting the same point twice. So we would either include it here and not, or include it there, but not both. Okay, so look at this. At x equals 0, does that look like it's continuous? Okay, that's the easy part. But the justify part, you can't just say, well, it looks continuous. Well, what does that mean? Well, it doesn't look like there's any breaks in the graph. Well, what do you mean by break in the graph? In math, we have to state it with the three-part definition. We have to say the limit as x approaches 0. We can either say it exists, or we can say that it's 0. I'll just say that it exists. The point at 0 exists. There's a point there. The limit exists there. And the number that it approaches from the left and the right is the same thing as the y value of that point. This is approaching 0, this is approaching 0, and this guy's y value is 0. That makes sure that it's in the correct spot and it's not just randomly way up there or way below it. So to prove something is continuous, we actually have to state all three things. The limit, it's not jumping around. The hole, or there's a point there, so there's not a hole. And then the last part, the number it's approaching on the left and the right is the same as the point that is there. The point is in the right spot. But when it's not continuous, we only have to name one of those. But to prove it is continuous, or to justify why we say it's continuous, we have to state all three. That's why it's important to memorize that. Okay, we got one more like this because, I don't know, I forgot to change this. This is 18 is really the same as 17, so we got one more like these. And then I think there's two of them for you to try on the other page. Actually, maybe not. There may not be any of them on there. Bless you. Okay, so let's graph square root of x minus 1. So if you don't remember what the square root of x looks like, then that's a little bit harder, but that's a piecewise, or I'm sorry, a parent function. You really should know what that looks like. And what is the minus 1 going to do?
Shift it right.
right, 1. So roughly like that. I want to make sure that I only keep it where x is equal to 1 and greater than 1. So that's actually the whole thing on this one. I don't have to erase anything. And then sometimes it's negative x minus 2. So that's like mx plus b. You've got a y-intercept. You've got a slope. But for this one, we only want to keep it when x is less than 1. So since it doesn't say equal to 1, we need an open circle there. And then less than 1 would be all the values to the left, but not the values to the right. Again, this is a function, so it should be passing the vertical line test. If I didn't erase this part, that should be a red flag to me because it wouldn't be a function. I know it's a function because it says it right here. F of x is a function. Okay, so the limit as x approaches 1 from the left, what does that look like? I agree. From the left, it looks like it's approaching -3, but from the right, it's approaching and if they're not the same, then that limit doesn't exist. So if I wanted to know, is it continuous at x equals 1? Well, again, most of the time you don't bother to do a graph. But since we have a graph, it's pretty easy to eyeball it and say, no, it's not continuous. We can see a big break in the graph. But to justify that answer, you have to explain how you know that it's not continuous. So you go through your list. You couldn't say the second part of the definition because there is a point there. But you could either state the first part or the third part. The limit from the left is not the same as the limit from the right. And again, to justify that it is continuous, you have to state all 3 parts, but to prove that it's not continuous, you just need to show one of them that's messed up. You don't have to list everything that's messed up. If it's approaching a different number, then your graph is jumping around. Okay, and then last question type I'd like you to see is a question similar to these two, but ones where you don't have a graph, because this is where it's a little bit harder for students to visualize what's going on. So the reason why this point was in the right place is because I carried x equals 0. X equals 0. So if you plugged in 0 into this, you got 0, and if you plug 0 into this, you got 0. So notice these two parts of the piecewise function. This guy and this guy never had the same y value. And even if they did, I don't care. I care right here at this point, at this time, that they have the same y value. This one, the first part of the piecewise function was at 0 when x is 0, and this one was at x equals 0, or y equals 0 when x is 0. So at this moment, I wanted this y value and this y value to be the same. Down here, I wanted the same thing to happen. At x equals 1, I wanted this guy's y value to equal this guy's y value, but it didn't happen. It went from this guy had a y value of 0, and then instantly on the other side of x equals 1, he had a y value of -3. So again, I don't care that they had the same y value way up here. Nobody's interested in that. I care, do they have the same y value at this, when it stops being the top function and starts being the bottom function. So I say all that because sometimes you're going to have something like number 19, or at least in calculus you will. I don't know that we put one of these on your test, where this has a's and b's in it. So as much as you may want to graph this, you just can't do that. It's abstract in a way where you can't visualize it. But what I know is that assuming a and b are numbers, this is continuous, and this is continuous. So to make the whole thing continuous, the whole piecewise function continuous, I need to make sure that when it stops being this function and starts being this function, that they're at the same place at the same time. They have the same y value. So we are going to set these two equal to each other. And just like the previous question, I don't care if they have the same y value most of the time. I need them to have the same y value at this moment when x equals 1, because that's when it stops being the top function and starts being the middle function. I need it to hand it off correctly. They've got to be in the same place at the same time so that there's not a break in the graph. So if we plug in 1 for x, we're left with that statement. A plus b is 2, so that gives us a hint about how big a and b need to be. But I've got to do the same thing for the bottom two as well. I don't really care what the middle function looks like, and I don't care what the bottom function looks like, but I need them to be in the same place at the same time. I need a plus b, ax plus b to be the same as 3x. Likewise, I don't care if they have the same y value normally, but I need to make sure they have the same y value at this moment. Because at this moment is when it stops being the middle function and starts being the bottom function. And I need to make sure it's handing it off correctly. So if we plug in 2 for x, we're left with that. So that gave us 2 equations and 2 unknowns, which is system of equations. So you could either solve this with elimination, which is what I normally do, or I'm sorry, substitution. Substitution is the one I usually do because that's the one that always works, and you use it 99% in mathematics. But I'm just going to do elimination in this one. That's where you like take one of the functions and just subtract away one of the other functions. So 2a minus a leaves you 1a, b minus b leaves you no b's, 6 minus 2 is 4. There's one part of your answer. And as soon as you know a is 4, you should be able to substitute it in here or substitute it in here and get b is -2. Then I guess since you think you know what a and b are, you could graph all 3 of these and then give yourself a visual to make sure that it's not jumping around. But like in calculus, when I tell students, this is the mistake they fall in. You set these two equal to each other and then plug in 1, and set these two equal to each other and plug in 2. That's all I really did. But the y is what sometimes they just overlook, and so then they don't remember it because they don't understand why they're doing that. I need these two to be in the same place at the same time when x is 1, because that's when it stops being this function and starts being this function. And then I need these two to be in the same place at the same time when x is 2, because that's when it stops being this function and starts being this function. So that's why I set them equal to each other and then either plugged in x equals 1 or plugged in x equals 2. So we really did the same thing up here. We just had a visual, so it was a lot easier to see. The number that we plug in from the left and right were both 0. Okay, so if you would take a moment to kind of scan through this, see if there's any questions you'd like me to follow up on, anything I could help clarify. Maybe see if there's any notes you want to write to yourself for when you look back at this. That all seems okay. How about this one? Does that seem really hard to y'all, or okay-ish? Again, I know y'all are going to be sick of me saying this if you're not already, but like in calculus, when I always talk about it's always the algebra that's difficult for people. Like I think in calculus, this is probably like 1 of 2 times all year that they have to do system of equations. But if you don't know how to solve system of equations, then that holds you back. So like, I mean, we can talk about it in calculus class for a minute or two, but if you don't remember it well enough that that's a reminder, then you basically have to go home and relearn that. So, but I feel like you guys usually do okay with that because you see it in Algebra 1 and Algebra 2, I think. Don't you do in Algebra 2 also? You don't remember? Okay. Okay, so I do want you to practice some of these and see how they go. And when I see that you guys have enough time, we can go over them together. I'll ask you for your answers, and then I can interject if it looks like you've got something different. You may notice that this piece of paper, like the graph and stuff, is pretty dark. I had our copy machine try to make this darker for you because one part of this doesn't print out very well, and that is this. So I need you to correct this on your paper real quick. Choice A, this is supposed to be 2 from the right and 2 from the left. So I made the image bigger to make it a little bit easier to see, but then it makes it that just not have good quality. So question 1, part A, right and left. Question 2, part A, left and right. Question 3, supposed to be right and left. It's just the plus and minus signs didn't copy basically. Number 4, same exact thing. One of them needs to be from the right, one needs to be from the left. And then last, I guess there's 2 more. Do the same thing on 5. Make one of them from the left and one from the right. And part A on number 6. One of them from the left and one of them from the right. Now, just to make sure you understand the directions, let's go ahead and look at question 1, and then I'll get out of your way for a few minutes and let you try them all. Okay, so one thing about this is it's not multiple choice in that you pick an answer, you choose all the answers that apply. Okay, so choice A, does the limit from the left of 2 and the limit from the right of 2, are those the same thing? Was that a no?
Yeah.
So don't pick that one. Does the limit exist?
No.
That's basically the same thing. Is there a point at x equals 2?
From the right.
Okay, so when x equals 2, y equals -4, that means there is a point there. So that should be one of your choices. And is it continuous at x equals 2? No. To be continuous, we needed this to be true, and this to be true, and we needed the third part of the definition to be true. So this is not true, and since there was one answer, you should not put none of the above. But it's not pick the best answer, it's pick all the answers that are correct. So, okay, so if you would try that on a couple more. Again, make sure you're paying attention to the directions there, and then the back page talks about different types: jump, infinite discontinuities, removable discontinuities. See if you know the names. And again, once I think you've had enough time, I will ask you guys to share out those answers, and I will stop you if it looks like something is off. And then I will need these today, so I can go ahead and put in the grade.
holes, so it can't be defined.
Oh, wait, no, we're on completely different holes. That's what I'm confused.
Yeah, no, yours.
Yeah, they're all right. Okay.
I was like, okay. I know, it's like,
Obviously, we're yeah. Yeah. Yeah.
That doesn't make sense.
It's basically just a whole since x equals 6. Huh?
It's just 6.
Yeah, for 8.
How'd you do it?
Huh?
Agree?
So that's a jump. Oh. Yes, I just didn't.
Like normally,
I
okay,
should've-
0.25,
yes,
I
you're
get it.
correct.
Like,
I didn't read the question very carefully. Guys, I was wrong on this first one. I didn't read it very carefully. Part A is true. It's not that they're equal. Oh. It's not that they're equal, but they do both exist. There is a number that this guy approaches and a number that this guy approaches. So we should have also picked A here. I just assumed it was talking about them being equal since that's what was going to matter, but I shouldn't assume that.
So even with the hole, they're both still approaching a number?
Yes, because limits don't care what's happening at that value. Limits care what it's approaching. Continuity also cares if there's a point there, but limits don't care about that exact x value.
So but to be defined at a certain number, you have to have one that's not a hole?
Correct. It means if I ask you what is the y value,
It's
just like broke.
Wow, that was so scary.
Oh my god, I'm still doing it.
Okay. That was so scary.
Why did you even walk though?
Because why couldn't I get up and walk? Oh my god.
is your foot asleep or something?
I don't know.
Her ankle just
Like
broke.
broke. I mean, it feels fine, but it was like,
Yeah.
I guess my foot had to have been asleep, but it didn't feel asleep. That was like scary. Why did you guys think
Well, it can't be, because you just said this.
Mr. Johnson?
Yep.
On 10, I don't know where the removable discontinuity is.
Well, removable is like the hole.
I know.
is on a jump.
Yeah, I know, but what, is there
That's
one,
like-
or is it x equal 2?
Here.
Oh, well, isn't that I'll say,
That your hole. If it just does it for a point, that's not a jump.
oh,
For a jump, it's like the whole function has to shift. If it's
Okay.
just for an instant, then that's still considered a hole.
okay.
You might have to just go directly to, yeah, that way you can, the weird part.
Which one, number 2? Yeah, no. No.
Okay, let's give everybody a few more minutes to get caught up and then we'll make sure that you guys are okay with that. Did anybody lose power the last couple days?
We did for like an hour.
It's not too bad. I saw a lot of people online that were out of power for a long time.
I was on for like 12 hours. It was at nighttime, so it's good.
That's one thing I like about my house is I live really close to the electric company, so like power never goes out because someone has to hit like a pole between us and them, and it's too short of a distance. So.
Most of the people that I know lost power were on East Fayetteville. Or
Yeah,
in
East
Fayetteville.
Fayetteville. I heard East was pretty bad.
Yeah.
Yeah, everyone got hit.
And some of our teachers live in Westport too, and places like that. If you lose power, it takes longer for someone to get out there.
Do you know the fingers in you trade?
No, I want to go over them first. I just making sure everybody had time to finish. We still got a few people working.
That's like your second day. Thank you. You're gonna have an awesome day. Hey, you gotta get the bad out of the way. You're gonna have to. That's fine.
This
That's the thing that never
why
happens.
is like
Yeah, he also like go all the time. I know. You like look back on the
Did you say that?
Yeah. Like you
No,
got
just
it.
don't last one, but that's not you.
Oh, so like come out. I was like, you didn't get up and get out. So
Oh,
you're
wait, yeah.
like, come out.
Probably 500.
And then you raise my ankle while I'm doing that. I wish I did just do that. Would be nice.
They also have, they just.
And that could be like every single day. It's like,
But maybe like
over
we
there.
can do that. Yeah, I don't know, like,
No,
do this.
yeah.
Oh, yeah, I would definitely.
You like Miss Reynolds?
Okay. Sure.
Okay, are we all ready? Okay, can we check these off so then I can grade them and we can be done for today? Okay, which ones were correct in number 2?
I said A and C.
Okay, I agree with A. I agree with C. That sounds good. Question 2, any questions? Okay, somebody else, tell me which ones you agree with on number 3. I agree. What else?
Wait, I thought it was whole, that's the only one
I don't think any of the ones are right.
Aren't they 2 holes?
So it's none of the above.
Limits don't care what's happening at that x value at all. You can completely ignore it. Limits are what y value is it approaching, not what y value is it at.
So then would B be correct as well as the rest of them?
Well, the limit doesn't exist because it's not approaching the same thing. I would say C's not true, correct? Because that's where that would matter. And lots of stuff that needs to be true is not true for being that, but there is something being true. So only A for number 3. Okay, somebody else for number 4. Which ones do you think will work? Or at least one of them? Okay, there is a point there. That is true. What else? B is true because it's approaching the same thing on the left and the right. Again, I don't care what the x value is. It's approaching the same thing from the left and the right. That's all limit asks. So A then 2. So if the limit exists and there's a point there, doesn't that mean D is going to be correct? Did y'all pick D or not? No, I agree. The point, the third part of the definition says that just because there's a point there and just because the limit exists, that point would have to be down here for it to be continuous. It's got to be what it's approaching from the left and the right has to be equal to what the point is. Okay, somebody else for number 5. Is A true? Is B true? Is C true? Is C true?
Yes.
And D? There's a point, the limit exists, and the point is equal to the limit. So it is continuous. All of those were true for number 5. And then last one like this. For 4, does the limit exist from the left and right?
Yes.
Are they the same thing? Is there a point for x equals 4?
Yes.
Just because that stuff's true doesn't mean it's continuous?
No.
It would only have been continuous if the point was up there. Okay, that's the last of that question type. Any of those you want me to repeat or explain again? Okay, the last parts are just about the different types. So this one, number 7, is asking for where is there a jump discontinuity. So that's where your whole graph is jumping. Looks like at -2. And that would be it. Number 9, which of these have an infinite discontinuity? Infinite is when your graph goes to -infinity and +infinity. X equals 5. So not horizontally. Your graph's going to go forever to the left and forever to the right usually. But that vertical spike, that vertical asymptote. Okay, and then 2 of these, because these are the ones that students often forget. Removable discontinuity is just basically the same as a whole. You just have to be careful not to accidentally pick out any jump discontinuity. So I see that this one has 2, 3, and 6. Whether that point exists somewhere else, or if it, like x equals 3, or if it doesn't exist somewhere else, like x equals 6, either way that is considered removable discontinuity. On number 10, I know it's tempting to maybe say -2 is removable because there's a hole right here, but the whole graph is jumping. So we refer to this as jump. We refer to this as jump. The only place that there was removable was x equals 4. So you might want to add a little bit to that, especially if you had any mistakes there. But what I will do today, since there's like 4 pieces of paper, I'll just come around and let you flip your pages around so I can see that you did all of it, and then I'll put the scores in, and then that way we can get those just done quickly. Good. Flip. Good. And notes. I need to see the practice and notes. Good. Thank you. Good. Good.
Yep. Good.
Cool.
Oh, it is supposed to be all this.
There's some names everywhere. That was awesome.
That-
Stop it. What's up?
Yeah, sounds good. Sounds good. What's up?
That's gonna like study. It's gonna be just the usual. I think we'll put a quiz on this stuff. Like before we do our unit test.
And you guys may want to staple those and get them put away in your binder too, just to keep it organized. But the first two we went over was 73, and then the last two was 74.